I was going to read proving and using pseudorandomness. That's true. But it's actually the number of BH sets of a given cardinality.
Thank you very much, Jack. Thank you very much to everyone for being here. Thank you very much to the organizers for inviting me and letting me speak. Right, so I will talk about the number of BH sets of a given size. So let's start with the definition, just to make sure. So BH sets and Sidon sets. So suppose you have a set A of natural numbers, and H is some fixed number. H during this talk will be always some fixed number, fixed integer. And so A is a BH set if you do the following. So you take all HY sums of elements of A. So A1 plus A2, AH. A1 up to AH members of A. So you produce all these HY sums, and if it so happens that they're all distinct, then you say that the set A is a BH set. In the case of H equals 2, this was introduced by Sidon, so they are known as Sidon sets. Okay, so the aim of the talk is to count these BH sets. So I would like to know how many BH sets there are in brackets n. So the sets A from the previous slide must be subsets of this brackets n. And again, this is asymptotic. H is fixed and n goes to infinity. Right, and the basic tool that we use to do this is we translate, very roughly speaking, we translate the problem somehow at some point to count independent sets in locally dense graphs. So these graphs are kind of quasi-random, or at least from below. So you know that smaller sets have at least some density. So this is the main tool that one uses. And this is joint work. So we have been doing this first for H equals 2 and then H equals 3 and so on. So we have been doing this with Domingos, Della Monica, Sanjun Lee, Wojtek Rodel, and Wojtek Samoti. Okay, so that's the aim. But let me start first with an associated extremal problem. So that is the following. So again, brackets n, so numbers 1 to n. Let's first ask how big a BH set can be if you take it from brackets n. So if this function fh of n is a naturally associated function, extremal combinatorial function, is the maximum size of a BH set contained in brackets n, right? So that's fh of n. Max of size of A contained in n, and BH set. Okay, so for the case H equals 2, as I mentioned before, Sidon explicitly asked the question to estimate fh of n. And so let me give a very simple argument that shows that fh of n is at most n to the 1 over h. You just do the following. So remember, to be a BH set, you have to take the HY sums of elements of curly A, right? So sums of the form A1 plus A2 and so on up to AH. Okay, how many sums can you produce that way? You can produce roughly kind of size of A choose H, because you have to select from your set curly A. Since you allow repetition, you actually get this size of A plus H minus 1 choose H. But it's roughly A choose H. And all these sums live between the numbers from 1 to Hn, right? Or H to Hn. So you have this inequality here. You have that A choose H, roughly A choose H is at most Hn, because all these HY sums have to be distinct and they live in this universe of size Hn. So you have this inequality. Then if you compute a little bit, you see that A is of size at most n to the 1 over h, with some coefficient which depends on h. You can get something like 2h if you like. So we get this upper bound for fhn, which is of the form n to the 1 over h. So that's this inequality 4. Right, so continuing a little bit. So for lower bounds, for this extremal function, Bose and Chawla have some algebraic construction, gave an algebraic construction which gives n to the 1 over h for this function with coefficient 1, or 1 plus little or 1. For h equals 2, you actually know that this coefficient is 1 plus little o 1, or you even know a little bit more than that. But in general, for h bigger than 2, you just know that it's of order n to the 1 over h, and the coefficient is not precisely known. And for the upper bound, the best bounds are due to Ben Green. But actually, I will not go into this direction. I'm interested in counting these sets, so let me not talk too much about this coefficient. Let me talk about the counting problem, the main problem I'm interested in right now. Okay, so we would like to count how many sets curly A we have inside the brackets n that are BH sets. So this will be the number ZNH. Actually, this question, the question of estimating Zn of H, was posed by Cameron and Addish in the case H equals 2. So this is the paper in which kind of they talk about such counting problems. They talk about several additive conditions for the set A, and they address the problem of counting such sets. And so here's the little section in which they talk about Sidon sets. So Sidon sets, again, so H equals 2, so the pairwise sums are all distinct, and that's what's written in parentheses there. Okay, and they argue, since you know that f2 of n, the extremal function is root n, you get these lower and upper bounds that you can see here, so 2 to the root n, for the lower bound, and n to the root n for the upper bound. So you have this log n in the exponent gap. And they ask, so what should be the answer to this? What should be closer to the truth? So again, fh of n is this extremal function, the maximal size. Then it's clear that 2 to the fh of n is a lower bound for the number of BH sets, because you fix a BH set. Every subset of this BH set is a BH set also. So that means that if you have a BH set of size fhn, then every subset gives you 2 to the fhn, obviously. So that's a lower bound for this, for the number of BH sets. It's a trivial lower bound. Everything comes from just one fixed maximal or maximum size BH set. And also, kind of trivially, you know that Zn of H can be bounded by all subsets of size at most Fn of H. And so these two bounds give, if you recall that Fh of n is of order n to the 1 over h, you get the following two bounds. Zn of h is at least 2 to the n to the 1 over h. And from above, you get n raised to the same power, or different coefficient. Or if you like, 2 to the constant times n to the 1 over h and log n. So that's 10, right? So you have this log n gap in the exponent with this simple argument. Okay. In fact, we can prove that the log n, which you saw in the exponent in the upper bound, is not necessary. So one can prove that that can be removed. So that's the first theorem here. So yeah, I'm just reminding that this is just to remind me that I should say again. So that we had these two bounds, right, with the log n gap in the exponent, and the answer is closer to the bottom side, kind of the trivial construction in which you take one BH set and all subsets. But of course, the coefficients in the exponent are all different and so on, but at least the order of the exponent is n to the 1 over h. Okay, now let's consider h equals 2. Let's talk about lower bound. And it's a little bit surprising that the lower bound is not of type 2 to the 1 plus little o 1 f2 of n. It's of that form, but with coefficient not 1, but this coefficient 1.16 at least. This is a little bit surprising because, for instance, I mean, there are such problems in the case of graphs. Maybe the oldest result is the following. So you could ask, how many graphs are there that are triangle free? Okay, so this, from the mid-70s, we know that the number of such graphs is something like 2 to the n squared over 4. And that you obtain by doing the following. So I have a graph on n vertices. I'm interested in triangle-free graphs, so one thing you could do is to take a balanced bipartite graph, n over 2, n over 2, and take all subset of the edges, right? So that would give you, yeah, well, I don't do this. So here I'm talking 2 and 2. You can take any subset of edges here that gives you a lower bound like this for the number of triangle-free graphs on n vertices. And in fact, this is the right answer, and this is known since the mid-70s. So it's 1 plus bit over 1 n squared over 4. So it's a little bit surprising that in the case of these Sidon sets, you don't get the coefficient 1 in the exponent. You don't get the coefficient 1 in the exponent, you get 1 point something bigger than 1, strictly bigger than 1. And this comes from some kind of blow-up construction or, yeah. Okay, but let me not discuss that. Okay. So I'm talking about upper bounds. I'm actually interested in a slightly more refined version of this counting problem. Namely, I would like to count not all BH sets contained in brackets n, but I would like the number of BH sets of a given size. So now we have a new parameter t, and we have this new function Zn h t, which is the number of BH sets contained in brackets n of size t. That's 14, right? So I'm interested in estimating this, and I'm interested in estimating this for a wide range of t. Okay. So this is, so what can we say from below at least, or let's try to get some feeling about the numbers that will show up. So the first thing is, so again, h is fixed, greater or equal to. Let's talk about t, which is not so big. So t, so in the Roman 1, so t is at most epsilon times n to the 1 over 2h minus 1. This exponent of n, this 1 over 2h minus 1, will show up kind of quite a bit now. This is kind of some critical point or critical exponent for this thing. Okay, so in this Roman 1, I'm interested in the case in which t is not so big. It says epsilon times this power of n. Okay, in that case, the number of BH sets is 1 minus delta to the t times n choose t. Of course, n choose t is all you could have, and a fraction of 1 minus delta to the t of them are actually BH sets. So again, what is the quantification? You can specify any delta. Then if you make epsilon small enough in the bound for t, you get this kind of 1 minus delta to the t fraction as BH sets. Okay, so it's a small fraction, it's exponentially small, but you can make the base of the exponent as close to 1 as you like. But then to do that, you have to pay by making t small in comparison with this n to the 1 over 2h minus 1. Okay, so that's this is the first remark. The second remark is that, okay, so you can ask what happens if you make t a little bit bigger. So maybe you're interested in t equal to 10 times n to the 1 over 2h minus 1. And actually, we can go up to, for this Roman 2 here, I will say the lower bound in a moment. You can go even some polylog factor above this power of n. Okay, and the bound that you get is again some fraction of n choose t, fraction of the universe. And this fraction is this e to the minus or something to the t. So previously I had some number close to 1 to the t. Now I have some number which goes to 0 to the t. And yeah, if you look at a little bit at this exponential, what's inside this exponential, it starts correctly. I mean, it matches, 14 and 15 match when you talk about constant times n to the 1 over 2h minus 1. Because if you kind of put t equal to constant n, this power of n, the n's cancel and you get some constant, right? But as you make t bigger or the constant bigger, this exponential, the base of this exponential goes to 0, right? Up to the point in which, so we're allowed to take t some polylog times the power of n, so you even get some power of n as a base of this exponential in this lower bound. So so again, as you make t bigger, this lower bound gets worse and worse, right? And that's what we have for the lower bound. Let me just very briefly try to say why you have such lower bounds. I will talk about Roman 1. So I'll talk about the case in which t is quite small. So epsilon times this critical power of n. So here's a rough sketch of the proof. Okay, we want to bound the number of t element BH sets from below. We start with the following simple remark. Suppose m is a new number. So suppose m is a lot smaller than n to the 1 over 2h minus 1, this critical power of n. Actually, and then do the following. Consider random sets of m elements taken from brackets n, completely random, uniformly at random. Now, this power of n, this n to the 1 over 2h minus 1, is chosen in such a way that if you do this, you can look into your random set and you can count how many forbidden things you have. What is forbidden? Forbidden, well, we are forbidden h-wise sums that have the same sum, right? Two different h-wise sums that give you the same result. Okay, so you can count those. And in such a sparse set, you don't have many of them. Actually, with high probability, such a set, random set brackets n m, can be turned into a BH set by deleting just a few elements. A few elements, I mean a small fraction of m. So you can remove some set t, which is little o m. So this random set, random m element set is kind of essentially all of it is a BH set. The numbers work out that way. Now you do the following. Remember, we are trying to bound this ZNH t. So you make m a little bit bigger than t, and you apply this observation, and you do the following count. Every m element set is essentially BH set. So for every random set, you have one BH set. But then when you do this, you have lots of double counting because two different random sets maybe have large intersection and they have the same, contribute the same BH set in your counting. So you have to discount this counting. So there's this, you divide by this binomial coefficient. And, and then you apply some elementary binomial identity. So you get this double counting thing gives you a factor. I mean, you have to divide by some, you have to divide n choose t by m choose t. And m is just a little bigger than t. So it's 1 plus epsilon times t. So this binomial coefficient is some exponential in t with the base, which is very close to 1. So that gives you the lower bound. Okay, so this gives some feeling at least why you have this critical point, n to the 1 over 2h minus 1, and why you can get this many, at least from below, at this range. Okay, now this fact 3 had a second thing, right? So I said you can make t a little bit bigger, and then you get this other bound. And to do that, you do something slightly more complicated to get the BH set given some random m set. And I will skip this. I will just mention that you use uncrowded hypergraphs, independent sets in uncrowded hypergraphs. Actually, it was the referee who kind of noticed that we say something which was a little bit incompatible with this fact 3.2. And the referee said, yeah, so maybe you should look at some old paper in which you use uncrowded hypergraphs to do this. And there was actually some paper in which we used this kind of method to obtain large C4-free graphs inside random graphs. But let me carry on. Let me not kind of discuss this. So far, I only spoke about lower bounds. So you have some idea about what kind of numbers you get. And here's finally the theorem, what we can prove. So again, h is fixed, and we have some small epsilon fixed. Then if t is big, so far I only spoke about t's which were below or just a little bit above this critical power of n, above by some polylog factor. But now I'm putting some extra epsilon in the exponent. Now that's the kind of t we can talk about in this theorem. And the bound is like this, is n over t to the h minus epsilon to the t. Okay, we should compare it with the lower bounds to have some feeling what kind of at means. So again, so here is the upper bound written in a slightly different way. I just factored out n choose t so that we can compare it with the lower bound. Okay, so it's n choose t times some exponential in t, some quantity exponentially decreasing with t, but actually the base of the exponential has a t in the bottom. So it really goes to 0 fast. And remember that when t is below this critical power of n to the 1 over 2h minus 1, then you actually had some exponential reduction, but the base was very close to 1. So this is the kind of 19 and 20 kind of show you the gap that you have before and after t crosses this critical power of n to the 1 over 2h minus 1. So yeah, probably it's not necessary, but we can say this in the following way. You suppose you have n choose t, and you select a random set of size t out of all possible sets, and you can ask yourself the probability that you will sample a BH set, and the probability that this happens changes really quite suddenly in the sense that, so you have these two bounds for t, right? And there's a dramatic change because in one case the probability is kind of some number close to 1 to the t, and in the other case, in the other case is t to the minus t. So there is some kind of change of behavior at this point. Okay, and actually when we were at the beginning of this project, we were interested in some different problem, and I'll talk very briefly about this other problem. We were interested in the following. Take a typical subset of brackets n, and we were interested in knowing how bigger BH set you can find inside this random set. So let me say it again. So a typical subset of brackets n, I will fix the cardinality. Now this is going to be m. So I consider all n choose m element subsets of brackets n, choose one uniformly at random, right? This brackets n index m means, sub m means such a random set. And I'm interested in finding inside this brackets nm a BH set of maximum size. So I want to know what kind of size you can find inside brackets nm. So that's the extremal function f of h brackets nm. We were interested in this function. Actually, this is a random variable, of course, because brackets nm is a random object. And of course, if n equals m, fh of n is, yeah. So this, you recover the original extremal function fh of n. And so the first easy remark, which we already actually used, is that if m is below this critical quantity n to the 1 over 2h minus 1, then most of it is a BH set. So this extremal function is kind of close to as big as it could be. So it's 1 minus little o 1 times m. And then the point is that if you go above this critical power of n, this should change. And in fact, the famous theorems by Colon and Gauss and Schacht, the transference theorems, actually tells you that this function fh n of m is little o m above this critical power of n. And we were actually interested in saying something about this function. And here's what we can say because of these, using these counting results. So now to say the result, I need to introduce some, let's start from the beginning. So again, h is fixed. And I have some piecewise linear function bh of a. So the function is this. Let me show you the graph of this piecewise linear function. It's here. So it's a piecewise linear function with this kind of three bits. This 1 over 2h minus 1 is the exponent of n that showed up quite a lot so far. Okay, so that's the piecewise linear function. Here it is. Now we do the following. So the theorem is fix some parameter a and consider m to be n to the a plus little o 1. A is any number between 0 and 1, right? But fixed. And now I'm interested in looking at random sets of size m. And m is n to the a. How bigger BH set can you find in such a random set? Okay, the answer is you get a BH set of size n to the BHA. And BHA is this piecewise linear function from 24. So let me say it using the graph. So we have a random set of n to the a elements. So in this graph, it would be like this. It would be kind of the diagonal, right? Your random set just goes up as a increases, right? And the size of the largest BH set inside it goes along with the diagonal, with the size of the set, up to this critical power of n, n to the 1 over 2h minus 1. And then it kind of stabilizes, stays flat, up to this second critical exponent of n. And then it kind of grows. But it doesn't grow at rate 1, it grows kind of at rate 1 over h. So this is the behavior of this extremal function on this random set. It kind of goes up and then flat and then goes. This was kind of the reason why we were interested and we found this problem interesting. Okay. So I'm out of time. And I will only say, I said that we do this counting by counting independent sets in graphs. Let me just say what the graph is. A bit quickly. So we want to estimate this ZNHT, right? And T is big. So the proof strategy is as follows. We start with some set S. S is a BH set. And S is smaller than T. And then we ask ourselves in how many ways we can increase S to a T element BH set by adding some set S prime to S. And to do that, well, as the starting set, the seed set has size comparable to n to the 1 over 2h minus 1. But then we do the following. We consider hy sum, so we consider 2h minus 2 elements, so a1 up to ah minus 1, and then b1 up to bh minus 1 from the set S, so they're already there. in the set S. And then now we consider two elements x and y. And if so happens that you have this identity, you have this 26, then you cannot put both x and y into your set S, or into your set S prime, which you are hoping to add to S to obtain a BH set. So one excludes the other. So you can just draw a graph joining x and y, and then you can search for independent sets in this graph, and the independent set will not let you put both x and y into the set x prime. So that's where the graph kind of shows up. Now I shouldn't try to say much about this. I should perhaps just say, so with this notion that one x forbids some y is encoded as a graph problem, and this graph is actually, for h equals 2, this graph is locally dense. You can show that any not too small set has enough edges so that the independent sets, there cannot be too many independent sets. So the graph is lower regular or pseudo-random, at least from below. But then for h equals 3 or bigger h, it's a lot messier. The graph is not, anyway, I will not try to say more than that. Actually, so I just skip to the end, because in the end I have a thank you slide. Thank you very much.
Okay, so are there any questions?
Okay, so you studied the question of course in the integers. Now you could ask the same question in vector spaces, right? Starting with subsets, all the h sums are different. Then you get some open questions in coding theory. Have you looked at those?
No, I haven't at all.
It's just the question of which bound is tight, the packing bound or the ending bound. It seems that you get the packing bound is tight.
Right, and you right. So you consider n to the d or zn to the, or zp to the d or something like that, and
in coding theory, those questions are wide open. It's interesting that you can get very tight results.
Yeah, thank you. No, I didn't. Right.
When you come to having to count the number of independent sets in your graph, do you use some kind of container method, or are you?
Yeah, right. Okay, so so there are slides about containers. But we cannot use containers, the hypergraph containers. We use just the graph case. Somehow this problem seems to be, there's something different, or, so we cannot use containers directly. We really have to mess around with the graph.
Okay.
Right.
Actually, I had one little question. So there's this beautiful result of Ruja that says that every set of size m in the integers has this subset of size m to the 1 over h, which is a BH set. So presumably that function is kind of lower than your BHA or...
sorry, let me see. So
that nice graph.
Yeah, so the graph... right. Yeah, actually, right. So
comparative purposes.
That's correct. So we can use what you just said for this bit here.
Right.
Yeah, right.
And there is an even line.
I'm sorry?
Even a dotted line.
Oh, this is just to show that the slope is... Oh, I see. You mean... so maybe that's Ruja. Okay.
I should, sorry. Okay, any more questions? If not, no, there is one more.
So could you comment why there is this flat part, where it comes from?
Because of the card. No. No, because... Right, so no, it's interesting.
So the beginning is just random.
Right.
Then there is this flat, cryptic flat, and then there is this obvious 1 over h. So I wonder what is the character of this flat part.
Yes, the lower bound... Yeah, so for the lower bound, I suppose if you're just interested in these, yeah, right, okay. So for the lower bound, maybe you can say in a random hypergraph, you know the size of the largest independent set, right? So Turan's theorem or something like that for hypergraphs. That gives you the lower bound. Right, but the fact that you have a matching upper bound, maybe says that when your size m is in that range, kind of that's what it is. It's random, and after the second critical point, your set must have some more structure or something like that. I don't really know.
You mean Turan and a 2H uniform?
Right.
Yeah.
Right. Something like that. Yeah. Actually, for h equals 2, we even computed more. So we even know there's some power polylog factor on top of this n to the BHA. So this little one, you can even write some polylog thing, and then you can use these uncrowded hypergraphs and so on. And they, at least for h equals 2, they match up to a constant, which is...
There are no more questions. Let's thank the...
Thank you very much.